Howdy, my name is Ross Current, and today we're going to be talking about phase diagrams. Some things we're going to cover in this video is what is a phase, the components of the phase diagram, given a temperature and alloy composition, we're going to be able to calculate the composition of the phases present and the concentration of the phases present, eutectic microstructures, and calculating eutectic composition. So, what is a phase? A phase is a homogeneous portion of a system that has uniform physical and chemical characteristics. So what does that mean exactly? So water and ice, they both have the same chemical formula, but they have distinct physical characteristics, so it's two different phases. And another example would be, pencil lead, so graphite and diamonds. They're both made of pure carbon, but how they're arranged, how the carbon atoms are connected to each other on an atomic level greatly defines their physical characteristics, making diamond very rigid and hard, and lead, or pencil lead, graphite, to be very soft and malleable. So, what are the components of a phase diagram? This is an isomorphous phase diagram because there's complete solid and liquid solubility between the two components. So there's a straight continuation of a solid phase on the bottom and a straight continuation of the liquid phase on the top. The bottom axis, the x-axis, is composition, weight percent nickel. So it means that the right side is 100% nickel and the left side is 0% nickel. And on the other hand, you could say that the left side is 100% copper and the right side is 0% copper. The y-axis is temperature. It doesn't have to be temperature. It could be a variety of things like density. This is the solidus line, and this is where the alpha phase, which is the solid composition or the solid alloy between nickel and copper, the solid phase, will begin melting at the solidus line, and it will complete melting at the liquidus line. Now we touch those. How many phases are present at point A? It's in the alpha region, so only one. And at the solidus line and the liquidus line, it's touching both the alpha region or the liquid region, depending, and the alpha plus liquid region in between the two red lines. So those two, as well as B, would be two phases. In point C, since it's only in the liquid phase, there's only one phase present. So, let's say we want to find out the composition of the alpha phase or the liquid phase at a point in this graph. So at a given weight percent nickel of 35% and a temperature of 1250 degrees Celsius, or at point B, what is the composition and the concentration of each respective phase at that point? So the way we do this is by drawing a tie line, which we start from the left, so we draw a line from B horizontally until we intersect the liquidus and the solidus line. and if we want to calculate the composition, we just draw another line from from each intersection straight down and read it off the graph. So the composition of the liquidus phase at point B is 31 weight percent nickel, and on the other side, the composition of the alpha phase at point B is 43 weight percent nickel. If we want to calculate how much of each phase or the concentration of each phase is present at this point, we use a lever rule, and the way that we start off by doing this is we divide up the the tie line into two separate parts, A and B, and then we call the total length of the tie line C. And the way we calculate the concentration of the alpha phase at B, or the concentration of a phase at a point, is you take the line segment that's on the opposite side of the point from the phase you're looking for. So if you're looking for alpha, it is the opposite side, so that's A, not B. A divided by the total length of the line. And if you were to look for the amount of liquid phase at B, you take the opposite line, which would be B, divided by C, the total length of the line. Pause it now if you want to look at the calculations. This is a binary eutectic phase diagram. Binary as in there are two distinct there's two distinct solid phases, alpha and beta, as well as a eutectic line, which is the horizontal bit, where the eutectic reaction occurs. So let's go ahead and point out the solidus lines on this graph, the liquidus lines at this graph, and the solvus line on this graph. This is the new line, and this is a line that intersects between alpha and alpha plus beta region. So the eutectic line is where the eutectic reaction occurs. And it's important because this eutectic is a mixture of substances that solidify and melt at the same temperature. So at this point, if you're starting at a high temperature, you decrease, all the liquid will solidify at this temperature into alpha plus beta phases. At this eutectic point, it's important, and I'll go into a little bit more depth later, because it doesn't enter any of these alpha plus liquid regions, but goes straight from the liquid phase to the alpha plus beta region. So at point A, how many phases are present? 2, alpha plus beta. It's in that region. And on the solvus line, how many phases are present? So it's touching the alpha region and the alpha plus beta, so still 2. As before, the solidus and the liquidus, look at each phase that they're touching on either side, and you'll see for the solidus line, there's 2 phases present. The liquidus line, there's 2 phases present. Now, what about the eutectic point? The eutectic point is touching liquid and the liquid phase and the alpha plus beta phase. So at this point, there's 3. This also goes for the whole length of the eutectic line. So the whole length of the eutectic line has 3 phases present. Now let's say we want to calculate the composition of the alpha phase at some point and the liquid phase at some point. So at this point, draw a tie line until we intersect the solidus, or liquidus line. We draw a line straight down from where we intersect the solidus line, and that is 17 weight percent tin. And straight down from the intersection with the liquidus line, which is 49 weight percent tin. Now if we want to do the concentration, same thing, we use the lever rule, and we divide this into 2 parts, with the total line being the length C. And if you want to calculate the alpha, or how much the concentration of the alpha phase at this point, we take the opposite line segment divided by C, and vice versa for the how much liquid phase. Pause it now if you want to look at the calculations. I'll be moving on. So we're going to talk about microstructures a little bit. So at point D, it's in the liquid phase. So if you were to take a magnifying glass or a really powerful microscope and really zoom in on this material, what would it look like at point D? It would just be a blob of liquid. So it's completely liquid. It's just a blob. And if we were to go down and pass through the liquidus line to point E, we'd begin to see some alpha phase begin to solidify within it. And after we pass the solidus line and reach point F, it's completely solidified, so it's completely alpha phase. But after we cross the solvus line, we start to enter the alpha plus beta region. So within this primarily alpha microstructure, we are starting to get little slivers of beta regions. So now let's say the same thing, but from a different point of the axis. This time, or a different point of the graph, and this time we're going to pass through the eutectic line, and I'll talk about that in a second. So at point J, it's completely liquid. As it passes through K, it's little bits of alpha begin to pop up. As you get closer down, more alpha begins to accumulate. Now we pass through the eutectic line to reach M. So the eutectic line is where all the liquid solidifies into a eutectic microstructure. So which ends up becoming, you still keep your alpha phase regions, which were there previously at point L, but the rest of it, the liquid, solidified into a eutectic microstructure, which is alpha and beta regions like little slivers mixed in. Now what happens if we go through the eutectic point itself? So if we go straight from point H, which is just solid liquid, and we go to excuse me, the point I, it completely solidifies into a microstructure without getting any alpha or beta blob, like solid blob or like blobs of phases like stuck in there. So it's pure microstructure. The reason why this is important, because if you were to look at on the left to a tensile strength versus composition graph, it's different components, but it's still the same idea. This point right under it is where you'll find the greatest tensile strength for materials for this composition. So it's really useful to know where the eutectic point is for real world application. Right there. So for eutectic structure, let's say we wanted to calculate how much was alpha, but more importantly, how much of or what composition is eutectic structure, which means more strength of the material, and how much and the concentration of it. So like how much of it. Same thing. At this point, we draw a tie line, but instead of intersecting liquidus or the solvus line from the alpha region to the beta region, we draw it from the solvus intersection all the way to the eutectic to a point right below the eutectic point. We do same thing before, straight down to find the percent compositions for alpha and the percent compositions for eutectic structure. And similar things for calculating the concentration of alpha in the eutectic structure, where we take A, B, and C. They calculate the concentration of alpha at this point is B divided by C, so the opposite line is 0.57, and they calculate the concentration of the eutectic structure at this point is A, the opposite line, over C, which is 0.43. So what did we cover? We covered a phase, the components of the phase diagram. Now with a given temperature and alloy composition, you should be able to calculate the composition of the phases present as well as their concentrations. We talked about eutectic microstructures and calculating eutectic composition. I know I went really quickly. Please go back and look over any of the calculations you were confused about. Thank you for your time today. Have a good one.